All right. So our experiment for this week is the geometric isomers experiment. And as I alluded to earlier, the focus of this experiment is actually determining which isomer we make in the lab. So we are comparing two different compounds, right? The first one is a nickel chloride complex that has two triphenylphosphine ligands. And the other complex that we are making is the thiocyanate complex. So these are both four coordinate complexes, right? And what we've seen so far in 481 is that the four coordinate geometry is actually a little bit more complicated for transition metal complexes because we aren't locked to just a tetrahedral arrangement, right? So if we look at these complexes, they actually have some commonality, right? So we can express both of these as nickel X2, L2 type complexes, right? So there's two X-type ligands and two L-type ligands. And that means that if we're focused on the geometry of our structures, we have actually three different options that we're going to look at, right? So the first is our kind of traditional VSEPR method, which is our tetrahedral arrangement. Right, so we have our tetrahedral arrangement here. And this is what we would expect from, organic chemistry and our early curriculum, right? Where the geometry for the tetrahedral shape is dictated by sterics, right? This is the furthest away that four different substituents can get from each other around a single center. However, as we move down in the periodic table, sterics become less important because our atoms get larger. So our bond distances get larger as well. And so electronic factors, right, can step in and change our geometry. And so the other case that we could imagine, right, is our square planar geometries. Right, here I could have a cis square planar arrangement, and I can also have a trans square planar arrangement. So these are my three options that I have in front of me for my four coordinate metal complexes, right? So if we just write out the molecular formula that I have up at the very top, it doesn't tell me anything about what geometry I have for my actual complex. So this lab is all about digging into and trying to differentiate, right, and study how can I make a claim about the geometry of a given complex, right? How can I decide which of these three options do each of these complexes fall into? Right? Are they both tetrahedral? Is one square planar and is one tetrahedral? Are they both square planar? Right? These are the questions that we need to answer in this lab. Which isomer do we have in front of us for our chloride complex and our thiocyanate complex? And so we're going to need to develop some new tools in actually answering this question, right? We currently don't have all the tools that we need in order to determine whether we have a square planar or tetrahedral complex. So let's look and see what these tools are going to be. And one thing I like about this lab and where it falls in our current curriculum is this lab is a great example for a couple different group theory applications. Right, so we're going to tie in our group theory knowledge of molecular orbitals in deriving our molecular orbital diagrams and our ligand field splitting diagrams. And then we're also going to use our new tool set for group theory that we're building this week to analyze the vibrations of metal complexes. All right, so up first is the difference between tetrahedral and square planar. So if we look at both of these complexes and we're thinking about the molecular orbitals, right, what we would first have to determine is our d electron count for our metal. So this is something we've been doing for 4 or 5 weeks now, right? So hopefully it's becoming second nature that you can find these d counts pretty quickly. So we look at the periodic table, we see that nickel is in that 10th column, right? So it brings 10 electrons to the party. Here I have two X-type ligands. That means that my nickel is a 2+ oxidation state. Therefore, both of these complexes are D8. And we're going to need this because, again, the first thing we're looking at is actually our molecular orbitals. And so when we're thinking about this, we need to have our d electron count in front of us. So these are both D8 metals. So why is this important, right? Our first step is distinguishing tetrahedral, right? Tetrahedral versus square planar. Right? This is the first thing we're trying to solve, the first question we are digging into. And the reason that this is important is that our tetrahedral ligand field, which we've derived in class now, right, has 2 lower lying orbitals and 3 higher lying orbitals, right? This is actually like the opposite of our octahedral field. And so we have this doubly degenerate set and this triply degenerate set that's up higher in our tetrahedral ligand field. Whereas our square planar arrangement, right, has a little bit more flavor to it. We have more of our orbitals that are spread out, right? And we have this differing influence due to the pi donor nature of our ligands themselves, right? When we have these strong field ligands, we have these really far spread apart orbital interactions. And so if we're going to go back and remember that these are D8 metals that we're discussing, we can look and see what these ligand fields might look like when we fill them in. Right, so if I'm going to put 8 electrons into my tetrahedral ligand field, there is no high and low spin state here, right? All I have is one configuration that's possible, or at least I should say there's not a low spin or high spin state that is possible for the ground state. I feel like I'm talking in circles. There's only one good ground state we can draw. There we go. That's what I'm trying to say. And then if we draw the square planar arrangement, again with my 8 electrons, right, that's enough to fill up 4 orbitals here. And so what I can see when I look at the difference between these ligand fields is that in a tetrahedral case, right, I have unpaired electrons in my tetrahedral ligand field. And this would mean that our tetrahedral complex is what we call paramagnetic. Right, and this refers to a system with unpaired electrons, right? So it has a net spin on our system. Whereas when we look at our square planar case, right, we have all of our electrons are paired up. The way we describe this is diamagnetic. And so there are no unpaired electrons in our square planar complex. And so if we're looking at these orbitals, right, this arrangement that we have in front of us, the question we would want to answer is, how can I study, right, how can I determine this number of unpaired electrons, right? If I gave you these 2 samples in the lab and I told you which of these has unpaired electrons and which one has all your electrons paired up, we don't have a good tool to do that, right? So our overarching question here, right, is how do we determine unpaired electrons? In the lab, I should say. Right, so if we're in the lab and I told you which of these is paramagnetic and which of these is diamagnetic, we don't have a great tool set in order to determine that. Right, these could both, be measured on the balance, maybe in the NMR, right? NMR, if you have these unpaired spins, they override the nuclear spins sometimes, and so you can't really get good NMRs of paramagnetic complexes. So NMR might tell you whether it's paramagnetic or diamagnetic, but we don't have a good way to determine which one or how to determine the number of unpaired electrons, right? We might be looking at other geometries where maybe we have 2 or 4 unpaired electrons, or like an example that we had on our first midterm, we had a case where we have 2 different spin states that were accessible at different temperatures. So how could we measure this, right? We need a method to determine the number of unpaired electrons. And so this is going to be our new tool that we have for this experiment, And this is a tool that's called magnetic susceptibility. Right, magnetic susceptibility. And as you might be able to guess right from the word, what this technique is based around is how much a sample's mass changes under a magnetic field, right? So that's really what we're looking at here, right? This tool that we're going to investigate measures, right? Let me pull up my definitions, right? So this measures a change in the effective mass under a magnetic field. And the really old school way that this was done is actually, it's kind of interesting if you ever like look up pictures of these things. But essentially there's a specialized balance. So you would get a mass of your sample on a table. And the table is a really important actually feature of the way that this used to work. Because you would get a mass of your sample and you would wheel a gigantic magnet underneath the table. And then you would see how the mass changes under this magnetic field. And so that was the old way of doing it. Now, what we do is there's a small machine that's in the lab. We have a very specialized glass tube, essentially, that we pack our sample into. You put it inside, and you can measure just the influence of that magnetic field within this smaller machine. Right? But the old way was a little bit more complicated. And so what we're going to be looking at here, right, our ultimate goal, like let's remember our ultimate goal, because we're going to rely on this a little bit. So our ultimate goal is to take a reading or a measurement and convert this to some number of unpaired electrons. Right? This is the goal we want to keep centered in our heads because this is actually not a simple process. It's not a one-step calculation. There's a few steps here that we're going to look at and focus on. And we want to keep this ultimate goal in front of our brains, right? That we want to take some kind of a reading or a measurement using this magnetic susceptibility and convert it into this number of unpaired electrons. So the way that we're going to do this is, again, starting with a reading, starting with what the balance will give us. And the first thing we're going to determine is something called the mass susceptibility. And the mass susceptibility gets this label chi-g, right? And what this represents is the relationship of the mass of our sample to this particular magnetic field. And this equation we're going to break into a few different parts. And I'm going to write it out a little bit differently than it appears in the PDF. Right, so all of this is in the PDF along with some guidance. So this isn't the only place you'll see it, but this is where I will kind of talk our way through it. So this is our equation that helps us determine the mass susceptibility, right? It has three different components here. So the first component is just a calibration. This is something that is used to make sure that the machine has accurate readings. This is something that you wouldn't normally be doing in the lab. This is something that I would do ahead of time. And after a handful of calculations and measurements here, this number comes out to be equal to 1 about 99% of the time, right? If I were to disassemble the machine and rebuild it, I would probably go through the calibration to make sure that it worked out correctly. But for our purposes, it's going to be equal to 1. This is kind of reminiscent of using Beer's law, right, where you had a path length that was always 1 centimeter, right? The path length in Beer's law was always really boring, but it's an important feature, right, of the actual measurement that we have. So that's our calibration, is this first step. The second step is the length of the sample in the tube divided by the mass. right? So like I said earlier, we have these specialized glass tubes, and you would load your sample into that tube, and it's a solid sample that's in here. And so we would measure out the length. And it's important that we make this measurement in centimeters, right? That's how this calculation is all set up. And we would use a balance, so we would get a mass of our sample. And what this ends up working out to be, right, this is kind of, right, if you squint and look at this sideways, which is always what I say, just to say, like, this is a fuzzy connection I'm making, right? This is kind of like 1 over the density of a substance, right? Density is essentially mass in a volume. And here we're looking at the length of that tube, right, is kind of our substitute for volume, but we still have our mass of our sample, right? What this is again describing is just how much compound we have that's interacting with our magnetic field. And it's important to note here that the mass of our sample ends up on the bottom of this equation, right? So this mass susceptibility is the interaction of this magnetic field per gram, right? Per gram is what we're looking at here. This final term that we have here is essentially a corrected reading. This is information that we would get off of the balance itself when we are making these measurements in the lab, right? So the first one here is the reading with our sample. And this R naught is just the reading of the empty tube. The reading of the empty tube is almost always about -34 is what this number works out to be. This is provided for you in the data tables, right, that have the information for you to process. So these tubes are very highly manufactured, right? They're tempered glass with no impurities that might interact with the magnetic field. That makes them very expensive, right? So each one of these tubes, it's a small glass tube. It doesn't look very fancy at all, but each one is in that ballpark of about $80. So normally when you're in the lab, right, this is where I hype up, like, be extremely careful with these tubes. Don't crack them or break them, right, because they're very expensive to replace. But now that we're doing this online, right, you can't actually break the tube. So that's a good benefit of being online, right? It's saving some costs here. So we have our measurements here that we can make. So now we can get to this mass susceptibility, right? Per gram, how strongly is my compound interacting with the magnetic field? But we want to go back to our ultimate goal, right? Our ultimate goal was not how much is our compound interacting with the magnetic field per gram. It's how can we get to a number of unpaired electrons, right, for my complex. So when in doubt, right, this is something that you should have in the back of your minds from all the way back in Chem 124 or Gen Chem, wherever you might have taken it, right? When in doubt, convert to moles. So we're going to do the same thing here. So our next step, we have our mass susceptibility. Our next step is going to be getting our molar susceptibility. Right? This is still chi. We just have a subscript m now to describe that this is the molar susceptibility. This has a much simpler equation. So we take that mass susceptibility we determined on that previous page, and we just multiply by the molecular weight of our compound. So this is how we've been going from mass to moles for years and years now, right? We want to remember that chi g, that term for grams, is actually on the bottom, right? So part of the units for this value would be per gram. That's why I'm multiplying here by the molecular weight. So now I have my molar susceptibility. So instead of per gram, now it's essentially per mole. How strongly is my compound interacting with the magnetic field? Again, we want to think about what we're trying to get to in our heads. In our heads, we're trying to get to a number of unpaired electrons, right? We're not trying to get to chi m. So we are still not done. right? We actually have 2 more steps in order to get to our number of unpaired electrons, because now we're looking at the molar quantity. But let's get down to an atomic level, right? Per molecule, per complex. How is this compound interacting with our magnetic field? So our next step is to calculate our effective magnetic moment. This describes our complex, right, and the individual complexes that we have in our sample and the way that they interact with a magnetic field. So this is mu effective that we're looking at here. And I'm going to write down the gnarly version of this equation first, and then thankfully we're going to simplify it down to something that is much, much, much easier to handle, right? So the full version, if you looked in your PChem textbook for this, is that we have 3 times the Boltzmann constant Kb times the temperature in Kelvin times chi A divided by Avogadro's number times the Bohr magneton squared, all of this to the 1/2 power. And this equation is actually written in the PDF. Thankfully, through a number of assumptions, we can actually simplify this equation down dramatically, and we can make our life a lot easier, because most of these things are constants or near enough to being constants that in our laboratory, we can treat them as if they were a constant. So this equation simplifies down to 2.828 chi m times T to the 1/2. So there are some assumptions that are made here in terms of the conversion that we're making, right, and lumping all of these constants together. But this version of the equation will work fine for us in terms of what we can do in 481 and 484. So what this has now done is this has now allowed us to figure out the effective magnetic moment, right? If we're thinking of the magnetic moment as a vector quantity, right? The net magnetic moment for a single complex. We have now determined that, right, from this reading that we make in the on the benchtop. So how can we finally get to our number of unpaired electrons? This is the final equation, the final step in this process. Right? How does the effective magnetic moment relate to our number of unpaired electrons? So this effective magnetic moment is equal to n times n plus 2, all to the 1/2. We can do some algebraic rearrangement here, and we can end up with the following equation. So if we square both sides and then lump all of our terms on the right, we now end up with a quadratic equation, which we can solve with a quadratic formula. And so now, right, now with this final equation under our belt, we can now finally get to a value of n, this number of unpaired electrons for our complex that we are studying, right? So we went all the way from a reading, we took kind of a winding road through these different values for our magnetic moments, and we can finally end up at a value for n that we solve using our quadratic formula. So there's one important note here, right? And reminding that we made a handful of assumptions. We made a handful of kind of leaps as we were simplifying our equation. So I'm going to take one step back and highlight something that's really important. This equation can break if chi m is negative. Right, and if chi m is negative, that means that some of the assumptions that we made were too dramatic in relating the magnetic moment of our particular complex. So if chi m is negative, this equation breaks because we can't get a square root of a negative number. So if chi m is negative, the effective magnetic moment you can assume to be equal to 0. Right, and this is kind of an important note that we're making here, right? This generally is true for diamagnetic complexes. So if something is diamagnetic, it actually repels that magnetic field a little bit, and you end up with a negative value for your molar susceptibility. So this is an important step, that if this equation breaks, if you end up with a negative value of chi m, assume that means that you have a mu effective of 0. Right, and this is where this equation will break. And then you can still go on and calculate the number of unpaired electrons from that equation. All right. So now with this in hand, we could go back and look at our diagrams from way back here. And we can see that if we do this calculation and we end up with a value of n equal to 2, right, 2 unpaired electrons, that would support the assignment of a tetrahedral geometry. And if we find a value of n equals 0, where we have no unpaired electrons, that would support a square planar geometry. So, like I said, our first question that we're asking in this experiment is how can we differentiate tetrahedral versus square planar in these complexes? Right, and so now we can do that. We can do that using magnetic susceptibility. So what is the next thing that we can do, right? How can we determine the geometry of our square planar complex itself? Right, so we said there's both a cis and a trans version of our square planar geometry. So we have our cis and our trans isomers. And the second thing that you're going to be looking at for this experiment is trying to make a guess as to whether you can even determine the difference between cis or trans with the information that's given. And we're going to actually be using vibrational spectroscopy to try to answer this question. So if we look at the difference between cis and trans, these are isomers of each other, right? These have different point groups that you'll need to assign. And we can actually use IR spectroscopy to determine the difference between cis and trans. So if we look at, let's say, just vibrations along our nickel X atoms, right, we can see that we have very different sets of vibrations, vibrational modes that involve these particular ligands. So our new video that was posted yesterday afternoon for class actually deals with how can we do this, right? How can I look at a ligand and try to say what is the vibrational mode of that particular ligand under these different point groups? So we can use group theory and we can use vibrational spectroscopy to differentiate between cis and trans, right? So we want to remember the ultimate goal of the lab, what we're doing from kind of beginning to end, is we have these complexes. You're presented with a good bit of data. You have IR data. You're provided with some UV vis data, which we aren't really going to be using for right now, and some magnetic susceptibility data. And it's your job to try to craft an argument, right, that assigns a geometry to each one of these nickel complexes. Are they square planar? Are they tetrahedral? How is it that you determine whether something is square planar or tetrahedral? And then if you have a square planar complex, you're going to analyze, can I differentiate between cis and trans? Right? What information do I have that I can use that might help me identify these different orientations or these different geometries of my structures? Right? Those are the big questions that we're digging into for this lab. Is how can we identify and support our identification of these geometries that we have in front of us? All right, so our main new tool is magnetic susceptibility, and we're also using group theory to determine these vibrational modes. You are asked for some specific things in terms of the group theory side that is going to tie in with our lecture from last week and tie in from lecture this week. So as I kind of alluded to earlier, this experiment falls at a good point in our class because it's really like a supercharged problem set for our group theory applications. So it has both molecular orbital stuff as well as vibrational spectroscopy, which are the main uses that we are going to see for group theory in Chem 481 and 484. All right, so that's what I had for us today. So like I said, on Thursday, we're going to talk more about the molecular orbitals that we can get from our calculations. But beyond that, that's what I got. So I've got office hours that are starting here in about 15 minutes. So if you have questions, you can always hang out or just come back then. And beyond that, I will see you in class tomorrow morning. So thanks for checking in, everyone. Have a nice afternoon.